Okay, we're doing a vector review. We already talked about basic definitions, and we're treating vectors analytically more than geometrically, meaning we're not drawing pictures so much. We talked about equivalence, or what equal means to vectors, vector addition and subtraction, and scalar multiplication. But how do you multiply vectors? Well, there's two common ways that have been defined. The first is called the dot product, sometimes known as the inner product. And here's all it means. A dotted with B, or A times B, I really shouldn't say times, because there's going to be two sort of multiplication type operations. A dotted with B means this arithmetic. Multiply the first two components, second two, and the third components, and then add them all up. Since we already went through matrices, if I took the vectors and made them column vectors, or say 3x1 matrices, it's the same as this matrix multiplication, A transpose B, so like that, either way. But here's how to do it. It's very simple. I'm dotting these two vectors. I get a -2, -6, plus 20. The result is 12. Dot products are easy to do. Talking of the standard basis, if I do, say, I dotted with I, go through that, I get a 1. If I do I dot j, I end up getting a 0. Same with I dot k. In fact, any of the standard bases dotted with itself will give you a 1. And if you dot it with either of the other two standard bases, you get a 0. Here's some properties. It is commutative. So A dot B equals B dot A. It's distributive. And by the way, A dot A, or a vector dotted with itself, gives you the squared norm of that vector. It'll always be greater than or equal to 0. An alternate form, this could be derived from the way we defined it using a law of cosines, or we could have defined the dot product this way and derived the other way that we defined it earlier. Either definition would work. And by the way, this theta is the angle between the two vectors. If I bring their tails together, it's that angle between them. So I have a way to calculate that angle, or that angle between them. The cosine is this in terms of analytic operations of the vectors. If the angle between them is 0, then the dot product is just product of their magnitudes. It's the angle between them is pi, meaning they're exact opposite directions, and it's just negative of the product of their magnitude. If that angle is pi over 2, meaning those guys are perpendicular, then the dot product is 0. And these notations mean if and only if, so it goes both ways. If the angle, well, if the dot product is positive, that means the angle is acute, 0 and pi over 2. If the angle is negative, that means, excuse me, if the dot product is negative, then the angle is obtuse, between pi over 2 and pi. Component and projection. Well, if you just wanted the component, using the standard bases, you would just dot it with the standard basis you're interested in. So A dotted with I would give you the first component, or the I component vector. And you could do that with any of the components of the standard vector. How do you do that in general? Not a standard vector, not a standard basis vector, but just any vector. Say, I want the component of A onto B, where A and B are given, vectors given to you. You drop a perpendicular from A onto B. You have this angle between them, and you call this length from here. If I put their tails together, the component is the length from here to A. That's what component means geometrically. The notation is the component of A onto B, and you can see it geometrically. That would be the length of A times the cosine of theta. We just had a formula for the cosine of theta. It was this A dot B over the magnitude product of A and B. So the magnitudes of A cancel. We have a formula for the component. A dot B over the norm of B, or you can think of it as A dotted with normalized B. Projection of A onto B is this vector itself. The component was just the length. The projection is this as a vector. Here's the notation. Projection of A onto B, and it's just that component of A on B, the magnitude, times the unit vector normalized, times the B vector normalized. This will give us something in the direction of B with the magnitude of the component. So we have a formula for the projected that ever comes up. I'll talk about cross product in a separate another record.